All right, well, we are going to tackle more 2D particle equilibrium. This time we're throwing a spring in, which makes things just a little bit more complicated. But we can get through this. You can do it. So what are we looking for? We have a 75-pound block here. It's supported by cable AB, spring AC. And we're trying to figure out what's our tension and the force. And then also, what's our unstretched length of the spring? So we're going to have to work towards all of that. I would say if we have a spring, just ignore that it's a spring. Treat this exactly like it's a cable until we know the tension in that. We can work through that. So the first thing I would do, if this was entirely cables, make a free body diagram. We know we're going to apply equilibrium. Let's just start out there. So we'll say our first step in here, number 1, is draw a free body diagram. We know that anytime we're making an equilibrium equation, we should have a free body diagram that ties in with it. We're building towards equilibrium on this. So again, let's make our free body diagram, starting out first. So we're going to draw that for the particle where everything connects in at, which is point A here. AB, AC, and the weight all connect at A. So let's circle around A, and we'll get our free body diagram drawn. Let's see if I can circle that better. Right about here. We are looking for that free body diagram point. So coming in here, anything that we cut through in this circle should show up as a force. So I cut AB, I cut the cable holding the weight, I cut the spring. So let's come down below and just replicate this picture. I have my point that I'm working with. This is point A. I know coming straight down from this, we have our weight, and it's given to us, 75 pounds. Anytime we have a cable holding up a weight, the tension of that cable should be the weight. So this is 75 pounds. There's nothing else I need to do with that one. I know that going up and to the right, I have cable AC, or spring AC. So let's put that in there. This is going to be, let's call this FAC, or TAC. We'll go with a T. TAC. Really, it's the same thing. Tension in spring AC. And we're given an angle for that. From vertical is a 30-degree angle. So come in and label a vertical line. This is 30 degrees. And then finally, our last unknown is we cut through cable AB on this. So let's come in and put that in there. So up and to the left, I have TAB. Kind of a shallow angle on this one. TAB. And we're given a triangle pieces for this, a 5, 12, 13 triangle. That's the angle it acts at. That's the ratio of height to base to hypotenuse. 5 for the height, 12 for the base, 13 for the hypotenuse. We can use that to figure out sine and cosine for everything. That's our free body diagram. Once I have that set up, we just want to come in and start working through our equilibrium equations. So we've done our first step. We have drawn our free body diagrams. We have all of that set up. So let's come in there and go to step 2, which is make our equilibrium equations. 2 equilibrium equations. And as we do that, we're going to solve these equations out. So make our equations and solve them out. So if I'm looking at this one, do I have one equation that I can set up and only have one unknown in here? Well, TAB acts in the x and the y direction, so no matter what equation I use, it'll show up in there. TAC also is acting in both the x and the y directions, so no matter what, it's going to show up as well. So I'm going to have TAB and TAC in all of my equations. I'm going to have to make a system of equations to solve this problem. That's okay, we can tackle it. It's 2 equations, 2 unknowns. It's a pretty doable thing for us. So let's just start out and choose one of our equations. I'm going to sum forces in the y first. So summing forces in the y direction. So if it points upwards, it's going to be a positive y force. Downwards is a negative y force. So we have TAC goes up. I want just the y component. That angle comes from vertical. Vertical, or y, is adjacent to my angle, so I need to use cosine. So I'm going to say I have TAC cosine 30. Gives me just the y component, that adjacent piece here, of TAC. I'll add into that TAB's y component. So plus, when I'm given the triangle pieces, I want if I'm doing forces in the y leg of the triangle divided by the hypotenuse. So 5/13 times my force, TAB. And then I can subtract off my known value in here, minus 75. And that's it. That's all of my forces. This is equal to 0 for us to be in equilibrium. Again, I have two unknowns in here, TAC and TAB. I can't totally solve this out, but I can reduce this down a little bit. I could get to cosine 30, I know is 0.866, so 0.866 TAC. 5/13 is 0.385, so plus 0.385 TAB. And let's move that 75 to the other side. Equals 75. And that'll be one of my two equations. Equation number one. One thing I would tell you to try to do, get rid of your trig identities in these fractions right away. Don't carry those through your work. No one really wants to deal with cosine 30 through all of their algebra steps. It's a bad habit to leave that in there. I get that your math classes probably want you to not round this off, and your math people are idiots. Round that number off. We would much rather, as engineers, work with a decimal in here. You're more likely to not make silly math mistakes if you have a decimal, because this is easier for us to wrap our head around than what does cosine 30 actually mean for us. Get rid of your trig identities, get rid of your fractions, round stuff off. It will help you be more successful, which is really what we're shooting for here. But from there, I can make my second equation. I can sum my forces in the x direction. So I don't need to include the 75 pounds in here. It's only in the y. TAC points to the right, so it's going to be positive, and the x component going to the right in here is opposite my 30-degree angle. Sine goes with opposite. So I need to use sine in here. TAC sine 30 minus 12/13 the x leg of our triangle divided by the hypotenuse times our force, TAB. That's going to get us to 0, equals 0 for equilibrium. Which again, let's reduce that down. I can move the 12/13 TAB to the other side, convert that to a decimal, and divide by sine 30. And I'm just going to get here that TAC is equal to 1.846 TAB, which is a second equation then. I now have two equations, 1, 2, two unknowns, TAC and TAB in both equations. That's a solvable system of equations for us. It's pretty easy for us just to substitute this in. So take that equation 2 and put it in. Anytime TAC shows up, we'll put in 1.846 TAB. So let's start up here. 0.866 TAC. We know TAC, though, is 1.846 TAB. Then we'll go back up above. Plus 0.385 TAB equals 75. Which we're down to just TAB as an unknown in here. Also, notice as we did this, we could have rearranged this to get to like a TAC equals or a TAB equals statement, but it's way easier if we take this equation and plug it into 1 than to try to solve 1 and plug it into 2. Do the easy approach for things. But solving that out, I'm going to get the TAB is equal to, TAB is equal to, where do I have it? 37.8 pounds. 37.8 pounds. From there, I can go in and try to get my next piece sorted out for everything. If I know TAB, I can substitute into either of these two equations and find TAC. Again, take the easy approach. You're going to be better off with it. Substitute into equation 2 will get us a lot easier to solve equation than substituting into 1. They should both get us the same answer, though. We can say that TAC, working with equation 2, is 1.846 times TAB. And I know TAB is 37.8 pounds. So times 37.8. Or that TAC is going to get us to 69.8 pounds. 69.8 pounds. With both of those known, let's come in and get our last piece. What's that original length? So our third step, find original length of the spring. So right now, to tackle that, we know, let's draw a quick triangle. We know this horizontal distance is 2 feet. Our hypotenuse here is LF, the final length. And we know this angle was given to us 30 degrees. 30 degrees. That gives me enough. I can actually find LF out from that. What's my final length of that spring? I can say that my sine of 30 sine is opposite equals opposite 2 over my hypotenuse, LF. Or solving for that final length, I need to, or I'll get that my final length is 4 feet. I can use that in my stretched length, where my stretch is my final length minus the original length. So I have LF, I'm trying to find LO, I just need to get the stretch. That one's pretty doable for us. I should know that the force in a spring is equal to a K value, which we were given, equals K times the stretch length. I found the force in here. That's my TAC value. I know my K value was given. I can find the stretch. Or my force is a known value for us. That force, 69.8 equals my K value, 60, times my stretch distance. Or this spring stretched, my S is 1.16 feet. Which means I now have my final length and my stretch. I can find the original length. 1.16, my stretch, equals my final length, 4 minus the original length. Which is rearranging that, moving LO over and 1.16 over. We're going to get to that original length in here. Had to be 2.84 feet. So when that 75-pound box was hung on everything, our spring elongated, settled into this equilibrium equation or in position, and got a little bit longer in there. But again, we can get through these problems. Particle equilibrium is a very important topic for us in statics. Make sure we can get these. Watch more examples. If this was useful, don't forget to like and subscribe to that so you get more of my videos coming out as we put them up. But good luck. You can get through this. You can do well on everything.